Hi guys, so I wanted to give you one last quick video that looks at some aspects of electromagnetic waves. Um, Gives you some simple relationships that you can use to investigate different situations and solve problems, and kind of wraps up our discussion on this topic. So, um, basically the last thing that we had looked at is that we compiled Maxwell's equations, and I made an argument to you through a derivation that you could extract the fact that Maxwell's equations support electromagnetic waves. And one of the last things that we had looked at with that was that the speed of these waves is given by, let me just say, this is E&M wave relationships. We'll look at a few different simple relationships. So the speed of these waves was given by the square root, 1 over the square root of epsilon naught mu naught. And it's pretty neat that when you put the numbers in, you find that this is equal to 3 times 10 to the 8th meters per second, and this is the speed of light. So it's pretty cool that these constants that we had been working with, the permittivity in the context mostly of capacitors, and the permeability, which we talked in most detail about inductors, you combine those constants together in such a way and you can extract the speed of light, which is pretty neat that Maxwell's equations essentially predict the speed of light. So one thing that I wanted to add to this is that remember when we were talking about capacitors, we modified epsilon. So where epsilon became a relative epsilon, which was equal to some dielectric constant times epsilon naught. In other words, ER was bigger than epsilon naught. Well, look at what will happen here if you put in a relative epsilon naught rather than epsilon naught. Since that number is bigger, this means that velocity, the speed of light, will be smaller in a dielectric. And this might seem weird off at first, but it's not. This is, think, for example, of glass. Um, the speed of light travels slower in glass, and that's responsible for, basically optics. All different kinds of devices are built exploiting the fact that the speed of light is different in a material. And one of the ways that you can think about that is that it is a consequence of the permittivity being modified in a material and being larger. And since the velocity is proportional to it's proportional to 1 over the square root of that, it's going to make larger permittivity is going to make the velocity smaller. And you could think of this in terms of the permeability too. It just happens that most of the materials that have a modified permeability are opaque, so we don't really see that. Although there are circumstances, special circumstances. Okay, so that was one relationship that I wanted to see you to see. It's just basically this generalization of the speed of light. So it's going to be less in a material. Another thing that you should be aware of is that the speed of light is also equal to the ratio of the electric to magnetic fields. And so if you look at the derivation in the text, it talks about, it motivates this for you. But this is kind of interesting because if you know the magnitude of the electric field and you know the speed of light, obviously, then you can pull out the magnetic field. And kind of the qualitative thing to take away from this is just that when you look at the magnetic field, notice that it looks like E over C. In other words, you can think of this as that the magnetic response is a lot weaker than the electric response. So, and by a factor of C. So it's just kind of an interesting relationship to consider when we've been talking about, like these electromagnetic waves. It can be kind of difficult to visualize, like, what does that mean exactly in terms of the strength of this response? And this is telling you explicitly that the electric response is stronger, or it's one way to think about it anyway. Um, okay, so I think this appears in your homework where they have you solve for one or the other. Um, Another relationship that you're going to make a lot more mileage out of, and I'll ask you about, is the fact that the speed is also equal to the wavelength times the frequency. So if you know the wavelength or the frequency, you can find the missing quantity. And this applies to the entire electromagnetic spectrum. So if you're reading the text, you'll notice there's a section on this. Basically, there's a lot of radiation that you might not think of as being electromagnetic waves. It's all electromagnetic waves, and it all obeys this relationship. So let me just paste in here actually a picture of this. One second. Hold up a second here. That. So this covers everything from, on the long wavelength end, things like radio waves, which can have wavelengths of greater than, hundreds of meters, to microwaves, to, infrared, which you think of as being like night vision. Visible light is just a small sliver. The electromagnetic radiation, the range that we're sensitive to, that we can detect with our eyes, is actually pretty small. Ultraviolet, so shorter than visible, which was why you wear sunscreen, right? To shorter wavelengths yet. Think of X-rays, gamma rays. All of this is all electromagnetic waves, and it all obeys this relationship that the wavelength times the frequency is equal to the speed of light. So let's look at a quick example. So it so happens that cell phones, they operate at different frequencies, but common cell phone frequencies are 850 and 1900 megahertz. And so if you want to know the wavelength of that, the wavelength will just be C over F, 3 times 10 to the 8th, divided by, 850, 10 to the 6th. So for 850, you would find that this would have a wavelength of about 35 centimeters. If you do this calculation for 1900 here, you'd find that this would have a wavelength of about 15, 16 centimeters. So, and this, you can see in this chart that appears here, it's it's between 1 meter and 0.1 meters. So, which is what we expect. So, and it's also, it should agree with kind of your intuition in terms of the devices that use radiation need to be of comparable scale to the wavelength of that. So if you think back to like old school cell phones that had to have antennas, that was to capture radiation that was on this sort of centimeter, fraction of a meter wavelength scale. So if you look at like radio towers, they operate at longer wavelengths. So the tower, the antenna is. In any case, this is just a simple example to get to point you at the relationship between wavelength, frequency, and the speed of light. Waves in general, but speed of light in this circumstance because we're talking about electromagnetic waves. Okay, so the last kind of topic, subsection that I wanted to mention is something called the Poynting vector. So, and this actually appears in section 31.8. And this is important because it tells you how much energy per time the electromagnetic wave transports per area. So in other words, this has units of watts per meter squared. And the Poynting vector is given by the following. It's proportional to the cross product of E and B. And so if we think about our vector math, what this is telling us is that this is going to be in a direction that's perpendicular to both E and B. So we know that E and B are perpendicular to each other, so far as I can draw that, which is not super good, but so basically if you apply your, your right-hand rule here to E and B, your thumb is going to be pointing in the direction of the Poynting vector, and that is telling you it's both the direction of energy transport, it's also the direction, the velocity of the wave. Now, a lot of times this is not the most convenient version of this expression to work with because you need to know E and B in their vector forms, and we also know that that E and B are perpendicular to each other when we're talking about transverse electromagnetic waves. So there are more convenient ways of expressing this. So let me just put here. This is not the most convenient form of this. For a couple reasons. You need E and B. And also, a practical reason is that the frequency of these waves is very large. So this is an instantaneous thing. This is telling you the power at any instant. But practically speaking, you can't measure this instantaneously because the frequency of an electromagnetic wave is too large. So really, it's better to talk a lot of times about an average. So we can recast this in terms of an average, and it will look like this. So what we're making use of here is a couple relationships. One is basically when we think about an RMS. So think back to when we were working with AC voltages and currents. You know that there's a simple relationship between the amplitude, the average RMS, or the RMS amplitude and like the peak amplitude. So that's what we're making use of here. And then we're also making use of the fact that we know that 1 over mu naught epsilon naught is equal to c squared. So you put these ingredients together and you can basically re-express the Poynting vector in terms of just the peak electric field amplitude. So this is, and like I said, we often work with the electric field because it's, you can think of it as being a stronger response than the magnetic field. So this kind of simplifies things, and this would be what you would end up using most often probably to solve problems, would be this form of the Poynting vector. Although there are other forms too, like you can write this in terms of the magnetic field as well, and it will look like this. Or you can write it in terms of both. And you can show that all these things are equivalent if you look at the RMS relationship and you look at this kind of stuff. And as well as the fact that C looks like E over B. Okay, so let's look at a quick example of this so that you can see a calculation. So let me paste in here an example question. So our example question, just a book question. The electromagnetic wave has a peak of 26, or so actually this should be millivolts per meter. 26.5 millivolts per meter. What is the average rate at which the wave carries energy across a unit area per unit time? So this would be, we would want to apply, notice it's giving us the peak, which is conducive to using this expression. So, and we're looking for the average, like I mentioned. So this will be equal to 1/2 times epsilon naught, so 8.85. Let's put in our units here too. So coulomb squared per Newton meter squared, times 3 times 10 to the 8th meters per second times the electric field. So it's given in volts per meter, but remember, we can also express this as newtons per coulomb, which is more convenient actually for what we're up to. So, and let's check the units here. So notice some of this is going to cancel. Coulomb squared, we lose a factor of newtons. If we look at what's left over, we're going to have newtons meters per second over meters squared. So a newton meter would be a joule per second, i.e. watts per meter squared. So power per unit area, which is what we were looking for with the Poynting vector. And if we crunch these numbers, you would find that the average value in this case would give you about 9 times 10 to the minus 7 watts per meter squared. So 0.9 microwatts per meter squared. And this is just an example of applying this Poynting vector relationship where we're just working with the electric field amplitude, and hopefully this helps you see like how you might approach stuff like this. So yeah, just sort of a few electromagnetic wave relationships that I wanted you to be aware of, and that's kind of more or less the last thing that you're responsible for.